So I am damn sure that you must have really understood the first two questions, their concepts and doubts related to it. So now let's look at question number 3. This is a bit lengthy question but very easy if you conceptually understand each and every term. So the first and most important part of every question, we need to analyze whatever the given data. So let's read the question. Water droplets fall in a cooling tower with air at 25 degrees centigrade, flowing at 5 meter per second over them, which is velocity is given to be 5 meter per second and temperature is given as 25 degrees centigrade. The droplets have an average diameter of 0.01 meter and are at 35 degrees centigrade. That is, the water droplets are at 35 degrees Celsius. Both heat and mass transfer occur simultaneously. So this is a statement. So what are the given data? Air properties are given at 30 degrees centigrade, which are viscosity. Viscosity is given to be 1.6 into 10 to the power minus 5 meter square per second. Prandtl number is given as 0.71. Also, we have water properties, water vapor properties. Smith number is given as 0.6 and diffusivity is given to be 2.4 into 10 to the power minus 5 meter square per second. So these are the given data. Now let's look at what we need to calculate. There are four parts in this question. Part A is we need to compute Reynolds analogy, Reynolds number for flow around a droplet. So this is the first part. In the second part, we need to use Chiltern-Coulomb analogy. That is, using Chiltern-Coulomb analogy, we need to calculate average Nusselt number and heat transfer coefficient. Also, we have one more part in that question, that is average Sherwood number and mass transfer coefficients. So both are similar, just we have a little difference. So we'll go to part C. In part C, we need to estimate the evaporation rate per droplet. Unit is given to be kg per second. If saturation concentration is 0.03 kg per meter cube. So saturation concentration is given. So the last part of the question is we need to justify why the analogy is suitable for spherical geometries in this case. So these are the four parts which we need to calculate.
So let's look into the solution of the given problem. In this problem, we have to find Reynolds number for flow around a droplet. In the second part, we need to use Chiltern-Coulomb analogy and calculate average Nusselt number and heat transfer coefficient. Also, in the same question, we need to find average Sherwood number and mass transfer coefficient. In the third part, we need to find the evaporation rate per droplet. The unit is given to be kg per second and the saturation concentration is given to be 0.03 kg per meter cube. And in the fourth question, we need to justify why the analogy is suitable for spherical geometries in this case. So let's start from part 1. In part 1, we need to compute the Reynolds number for flow around a droplet. So the given data for this part is air velocity is given, which is given as 5 meter per second. Droplet diameter is given to be 0.01 meter and kinematic viscosity is given to be 1.6 into 10 to the power minus 5 meter square per second. So you are now familiar with the Reynolds number and its formula. Reynolds number is given as U into D divided by kinematic viscosity. Substituting all the given values, we get Reynolds number to be 3125. Now, as the Reynolds number is between 20,000 and 3125, the flow will be transitional flow. That is, it will be neither fully laminar nor fully turbulent. This type of flow is known as turbulent, is called transitional flow regime. So this is basically an overall idea of part 1. So let's move to the next part. In the next part, we need to calculate Nusselt number and heat transfer coefficient. So first of all, in this part, we need to use Chiltern-Coulomb analogy for heat transfer. You all are familiar as we have derived this formula. So the formula goes as Stanton number for heat transfer multiplied by Prandtl number to the power 2 by 3 is equals to F by 2. Here F is nothing but friction factor. Now we have introduced a new correlation, that is Rance-Marshall correlation, and this is basically for spheres. The formula is Nusselt number is equals to 2 plus 0.6 multiplied by Reynolds number to the power 1 by 2 multiplied by Prandtl number to the power 1 by 3. Now all Reynolds number we have found in part A. Prandtl number is given in the question, which is 0.71. So substituting all the values, we get Nusselt number as 2 plus zero point 0.6 plus 3125, that is Reynolds number, to the power 1 by 2, multiplied by Prandtl number, that is 0.71 to the power 1 by 3, which is equals to 2 plus zero point 0.6 into 55.9 multiplied by 0.89. That is the final answer for Nusselt number comes out to be 32. So this is the solution for part 2. Continuing further, we also need to calculate heat transfer coefficient. Now, heat transfer coefficient, this formula is very easy. H is equals to Nusselt number multiplied by thermal conductivity divided by diameter. So, H is equals to Nusselt number, as we just found in previous part, is 32, multiplied by thermal conductivity is given in the question, which is 0.026 divided by diameter, that is 0.01 meter. So calculating this, we get heat transfer coefficient as 83.2 watt per meter square Kelvin. Let's move further. In the part C, that is the third part, we need to calculate Sherwood number and mass transfer coefficient, that is Km. So similarly, as we use Chiltern-Colburn analogy for heat transfer, here also we will use Chiltern-Colburn analogy, but this will be for mass transfer. Just a few changes in dimensional numbers, or else the formula remains same. The formula goes as Stanton number for mass transfer multiplied by Smith number to the power 2 by 3 is equals to F by 2, where F is as previous friction factor. Now, Rance-Marshall correlation. We have used this correlation in the previous part, and this goes for Sherwood number as 2 plus 0.6 multiplied by Reynolds number to the power 1 by 2 multiplied by Smith number to the power 1 by 3. Now, we have calculated Reynolds number and Smith number. Smith number is given in the question. So we will substitute all these values, and finally we get Sherwood number, that is 2 plus 0.6 multiplied by Reynolds number, that is 3125 to the power 1 by 2 multiplied by Smith number, that is 0.6 to the power 1 by 3, which is equals to, after calculating, we get Sherwood number as 30.2. Next, we need to calculate mass transfer coefficient. Mass transfer coefficient is given by simple formula, that is Sherwood number into diffusivity divided by diameter. Sherwood number we have calculated, that is 30.2. Diffusivity is given in the question to be 2.4 into 10 to the power minus 5 divided by 0.01, that is the diameter, which is in meter. So after calculating this, we get mass transfer coefficient as 0.0725 meter per second. So I hope you are clear until this. Next, the fourth part is to estimate evaporation rate per droplet. Here, the given data from the question is that saturation concentration, that is CS, is given to be 0.03 kg per meter cube. We assume bulk concentration C infinity, and it is to be 0 kg per meter cube because of dry air. So now we need to calculate molar flux. So molar flux is given as Km multiplied by Cs minus C infinity. Cs is nothing but saturation concentration, and C infinity is nothing but bulk concentration. Now Km we found out to be 0.0725 multiplied by 0.03. This comes out to be 2.175 into 10 to the power minus 3 kg per meter square second. Be careful of the units. If you don't write units, there is no sense in solving the question. Next, we need to calculate surface area of droplet, which is denoted by capital A. Now, surface area is given by pi d square, which is equal to pi into 0.01 square, which comes to be, that is, area comes out to be 3.14 multiplied by 10 to the power minus 4 meter square. Now, after calculating molar flux and surface area of droplet, we simply calculate evaporation rate, that is, just multiply these two terms, that is molar flux multiplied by the surface area of the droplet. Now, the final value of evaporation rate comes out to be 6.83 multiplied by 10 to the power minus 7 kg per second. Let's move further. The last part of the question is why Chiltern-Colburn works for spheres. Now, there are 3 points in this solution. The first one comes out to be empirical validation. The Rance-Marshall correlation. Now, this correlation we have used in the 2 parts of our question. that is Sherwood number is equals to 2 plus 0.6 multiplied by Reynolds number to the power 1 by 2 multiplied by Smith number to the power 1 by 3. Now this is derived from the experimental data for spheres. So this is the first point. The next point is boundary layer similarity. Heat and mass transfer at the droplet surface follow analogous boundary layer physics. The last condition or the last point is limitations. Low Reynolds number dominated by diffusion, that is Sherwood number is approximately equal to 2, and high Reynolds number, that is for Reynolds number greater than 20,000 it requires turbulence models. Now the key assumptions that are used in this part is no internal circulation within droplets, that is there is no internal circulation within the droplets, and the next assumption is negligible radiation and chemical reaction. This means there is no chemical reaction. Next, now the overall summary, that is key results from all these parts, is that first we found out Reynolds number. The Reynolds number came out to be 3125 and the flow was neither turbulent nor laminar. It was a transitional flow. Next, we found out Nusselt number, which came out to be 32. We found out heat transfer coefficient, whose value was 83.2 watt per meter square Kelvin. Take care of the units. Now next, the dimensionless number was Sherwood number, which came out to be 30.2. And next we found out mass transfer coefficient, which is denoted by Km, to be 0.0725 meter per second. And finally we found out evaporation rate, which was multiplying flux into area, which came out to be 6.83 into 10 to the power minus 7 kg per second. So this was the step-by-step analysis of all the 4 parts given in the question. So be very conceptually strong to solve such types of questions, because if you miss any given data or any key concept, you are more likely to make major mistakes. So I hope you understood this question.
So now let's move to our last numerical of this podcast, which is optimizing a chemical plant's air stripping tower. The scenario is explained as a chemical plant uses an air stripping tower to remove acetone vapor from wastewater. The air is at 25 degrees Celsius and 1 atm, which flows over 0.5 meter into 2 meter wetted plastic plates at 12 meter per second. The acetone concentration at water-air interface is 0.02 kilomole per meter cube, and goal is to determine the acetone removal rate per plate in kg per hour. The given data in this question is air properties. Kinematic viscosity is equal to 1.6 into 10 to the power minus 5 meter square per second. Prandtl number is given as 0.71. Smith number for acetone air is given as 1.8, and the diffusivity is given as 8.2 into 10 to the power minus 6 meter square per second. Also, the plate dimensions are given as length is equal to 2 meter and width is equal to 0.5 meter. Now, let us analyze how we are going to calculate, or how we are going to answer this question. First of all, we are going to calculate the Reynolds number and determine the flow regime. Next, we are going to calculate the Sherwood number using Chilton-Coleman analogy, and then we are going to calculate the mass transfer coefficient. So by calculating all these three, in the end we are going to calculate the acetone removal rate. That's all.
So I'm damn sure that you must have understood the problem and all the doubts related to it. Now let's look at the solution part by part. Part A of the solution states that we need to determine flow regime. For that, we need to calculate Reynolds number. Reynolds number is given by the formula. As we all know, it's velocity into length divided by kinematic viscosity. All these terms are given in the problem. Velocity is given as 12 meter per second, length is given as 2 meter, and kinematic viscosity is given to be 1.6 into 10 to the power minus 5 meter square per second. As we know, Reynolds number is a dimensionless quantity. Therefore, it comes out to be 1.5 into 10 power 6. As the Reynolds number is greater than 5 into 10 to the power 5, we get turbulent flow. So therefore part A gets finished. Now let's look into part 2. In part B we need to find Sherwood number. For that we need to use Chilton-Colville analogy for turbulent flow. The formula for friction factor of turbulent flow is given by 0.074 into Reynolds number power minus 1 by 5. Substituting all the values of Reynolds number, we get 0.074 into 1.5 into 10 power 6 whole power minus 1 by 5. Calculating this, we get final value of friction factor as 0.0034. Now we have found friction factor which came out to be 0.0034. Now with the help of friction factor we find Sherwood number. So we compute Sherwood number by the formula. Sherwood number is friction factor divided by 2 into Reynolds number multiplied by Smith number power 1 by 3. Substituting all the values, we get equation in the form 0.0034 divided by 2 into Reynolds number which we found in part A, which is given as 1.5 into 10 power 6 multiplied by 1.8 power 1 by 3. Calculating all this, we get final Sherwood number as 3240. Now with the help of Sherwood number, diffusivity and length, we calculate mass transfer coefficient. Mass transfer coefficient is related to these terms as Sherwood number multiplied by diffusivity divided by length. So Sherwood number we calculated just here, which is 3240. Length is given as 2 meter and diffusivity is also mentioned in the question, which is 8.2 into 10 power minus 6. Substituting all the values, we get mass transfer coefficient as 0.0133, which has units of meter per second. So after solving part A, B and C of the question, we will now move to part D. Part D in the question, we need to find acetone removal rate. Acetone removal rate. In order to find acetone removal rate, first of all we need to find molar flux. Molar flux is denoted by Na. And the formula to find molar flux is given by mass transfer coefficient multiplied by concentration difference, which can be written as Na is equals to mass transfer coefficient into concentration difference, that is concentration at the surface minus concentration at bulk, that is bulk concentration. Substituting the values, mass transfer coefficient we have calculated in previous parts and it is given as 0.0133 multiplied by the concentration at the surface is given to be 0.02 and bulk temperature is assumed to be 0. Calculating this, we get value as 2.66 into 10 power minus 4. Now with the help of molar flux, we find a rate, that is total rate per plate, which is the solution. Total rate per plate. It also rhymes. Now the formula for finding rate is given as Na, that is molar flux into area into molar mass multiplied by time. Now according to the given data, we know molar flux is calculated to be 2.66 into 10 power minus 4. Area is given to be 2 into 0.5 meter square. Molar mass is given in the question as 58.08 kg per kilomole. And the last time is given as 3600 seconds. that is 1 hour. So substituting all these values, we get the final answer for the total rate per plate to be 55.6 and the unit is kg per hour. So this is the total rate per plate which we need to find, and we have calculated it in the part D of the question.
So, as we have come to the end of our podcast, let's take a moment to reflect on the importance of what we have covered and let's conclude our podcast. So, the topics covered in our podcast are Reynolds analogy, Chilton-Coleman analogy, and numericals based on these two analogies. We also saw the physical interpretation of friction factor, heat transfer coefficient, and mass transfer coefficient before deriving these two analogies. We saw how Osborne-Reynolds derived the Reynolds analogy using the connection between heat and momentum transfer. We also saw the Chilton-Coleman analogy's expression and derivation. We also saw the parameters that are related to these two analogies such as Nusselt number, Sherwood number, friction factor and other terms. In, in this podcast, so to summarize, in this podcast, we explored two fundamental analogies that bridge the gap between momentum, heat and mass transfer, the Reynolds analogy and the Chilton-Coleman analogy. So, whether you are designing a heat exchanger, optimizing a reactor or modeling a cooling system, these analogies provide a solid starting point. They show how deep the connection run between seemingly different physical phenomena. Thank you.